In this video, we're going to cover section 1.19, photochemistry. Molecular photochemistry is a science concerned with the structures and dynamic processes that result from the interaction of light with molecules. Two of the most fundamental components of the universe, photons and molecules, interact with one another to produce electronically excited molecules, which are eventually transformed into isolated products. The field of molecular photochemistry is classified in terms of the photophysics and the photochemistry of molecules. Photophysics involves the interaction of light and molecules resulting in net physical changes, whereas photochemistry involves the interaction of light and molecules resulting in net chemical changes. Photochemical reactions are important in a wide variety of areas. For example, the primary event in vision involves the absorption of a photon by the visual pigment rhodopsin. Further, photosynthesis involves the conversion of light energy into chemical energy by plants and bacteria. Other areas include photodynamic therapies, which are used in cancer treatments, laser microsurgeries, which reduce scar tissue, photolithography, photopolymerization, fluorescent sensors, and photochromic materials, a topic that we're interested in our lab. Now, when a molecule absorbs a photon of light, the energy contained in the photon is transferred to the molecule. The amount of energy contained by a photon is given by the Planck equation, where the energy of the photon is equal to h nu, where h is the Planck constant and nu is the frequency of light. Now, the frequency of light can also be calculated from the speed of light, c, and lambda, the wavelength of light at which absorption occurs. Now, a mole of photons is referred to as an Einstein, and the energy contained by an Einstein of photons is the Avogadro number times the energy of a photon, as shown in this expression. In photochemistry, we are often concerned with the energy difference between two energy states of the molecule. We refer to this energy difference as the energy gap given by delta E. We're concerned with this energy difference rather than the absolute energy of any one state. And so delta E is the difference between two energy states of the molecule. In photochemistry, these are the electronic states of the molecule. Now, the absorption of light may occur when the photon energy is equal to the energy gap between two electronic states of the molecule. For example, the weakest single bonds have strengths of approximately 150 kilojoules per mole. This is typical of an oxygen-oxygen single bond. And the strongest single bonds have strengths on the order of 420 kilojoules per mole, typical of an oxygen-hydrogen single bond. Now, these energies correspond to photons with a wavelength of 420 nanometers and 290 nanometers. So here's a question. If a germicidal mercury lamp emits UVC light at a wavelength of 254 nanometers, and if this lamp can be used to excite electronic transition between the pi and the pi star of 1,3-butadiene, how much energy does this electronic transition correspond to? Well, to solve for this particular question, we're going to take the wavelength of light and we can substitute it into our expression for delta E. We have three constants divided by 254 nanometers. That will give us our delta E and the energy corresponding to this electronic transition. Based on these two examples shown here, we would expect the energy of a 254 nanometer transition to be greater than what we observe for 290 nanometers. So we expect the energy difference to be greater than 420 kilojoules per mole. But I'll let you go through that calculation to see for yourself. Now, the wavelengths of greatest photochemical interest are between 200 and 1,000 nanometers. 200 nanometers is the practical cutoff in the UV region due to the absorption of quartz. Quartz is a material, silicon dioxide, that is often used to make cuvettes in absorption spectroscopy. Below 200 nanometers, quartz starts to absorb, so that makes it very difficult to carry out absorption spectroscopy of the sample. Whereas above 1,000 nanometers, this tends to excite molecular vibrations rather than electrons. Now, this photochemical range can be further subdivided into three particular regions: the UV region, which spans 200 to 400 nanometers, the visible region, of which we see 400 to 700 nanometers, and the near-infrared region from 700 to 1,000 nanometers. But this photochemical region is really only a sliver of the entire electromagnetic radiation range, which extends from gamma rays, cosmic rays, all the way up to radio frequency waves. Now, the highest energy photon corresponding to a gamma ray with a wavelength of 0.0001 nanometers and a frequency of 3 × 10⁻21 per second, the energy of an Einstein of gamma photons is on the order of 1.3 × 10⁹ kilojoules per mole. Now, at the other end of the spectrum, the lowest energy photon corresponds to a radio frequency wave with a wavelength of approximately 1 × 10⁻10 nanometers and a frequency of 3 × 10⁶ per second. The energy of an Einstein of RF photons can be equated to about 1.3 × 10⁻⁵ kilojoules per mole. I mention this to show you the range in energies that we observe in the electromagnetic spectrum. There are 14 orders of magnitude difference between radio frequency waves and that of gamma rays. So this figure represents the electromagnetic spectrum, where we have our radio frequency waves at one end of the spectrum and our gamma and cosmic rays at the other end of the spectrum. And again, our photochemical range of interest spans from the near infrared to the ultraviolet, including our visible. And this is where we predominantly see electronic excitations, our photochemical events. Now, if we go to lower energies, longer wavelengths, lower frequencies, we move beyond electronic excitation, and we basically are inducing molecular vibrations, and then at lower energies still, molecular rotations. Whereas if we go to higher energy, higher frequency, and shorter wavelengths, we start to move away from electronic excitations, and we move into the core electron excitations, and then excitations within the nucleus. Now here's another figure showing you the corresponding bond energies associated with different wavelengths of light in our photochemical range. So again, our oxygen-oxygen single bond are some of the lowest energy bonds associated with photochemical events, whereas the OH and CH bonds are some of our strongest bonds that we observe in photochemistry. In addition, this figure reminds us that once we get out of our photochemical range and enter into the infrared region, we start to move away from electronic excitations within molecules and more or less are inducing vibrational excitations in molecules. Now, the simplest photochemical process is the absorption of a photon by a reactant, resulting in product formation. And that's shown by this scheme here, where A is interacting with a photon with an energy of h nu, and eventually we're transforming that reactant into product. Now, the rate of reactant photoexcitation, that can be given by the following expression, where I abs represents the intensity of absorbed light in the units of Einstein per centimeter square per second. 1,000 represents a conversion factor from centimeters cubed to decimeters cubed. And this is all divided by the sample path length, which is in centimeters. Carrying out this conversion is going to equate our rate to the units molar per second. Now, according to the Beer-Lambert absorption law, the absorbance A of a sample is given by the following expression, where A is equal to minus log of I trans over I0, where I trans is the intensity of light transmitted through a sample, and I0 is the intensity of the incident light, the light that's irradiating the sample. Now, this expression can also be equated to the molar absorptivity of the species A, the path length, and the concentration of the species A. Now, we can rearrange this part of our expression. If we take the negative sign over to the right, and if we take the antilog of both sides, and then multiply through by I0, we end up with the following expression, where I trans is equal to I naught times 10 to the exponent minus epsilon L concentration of A. Now, since the intensity of light which is absorbed by the sample is the difference between the incident light and the intensity of the transmitted light, we can substitute in I trans into this expression. And that gives us the following, where I abs is equal to I naught minus I naught 10 to the minus epsilon L concentration of A. Now we can factor out I subscript 0 or I naught, and that leaves us with this expression. Now, if the concentration of A is kept small, only the first two terms in the series expansion of the exponential term are appreciable. So our exponential term can be equated to these two terms, 1 minus 2.303 epsilon L concentration of A. So if we now substitute in for this in our previous expression with these two terms, we end up with the following expression for the intensity of absorbed light. And finally, if we substitute this expression into the rate expression for reactant photoexcitation and integrate, it yields the following. And note how this form of the expression is identical to the form for a first order reaction. This shows that the absorption of light will result in the decay of reactant concentration consistent with first order kinetic behavior. Most photochemical reactions are first order in reactant concentration, such that this equation describes the evolution in reactant concentration for the majority of photochemical processes. This scheme nicely describes the various pathways that we typically observe in molecular photochemistry. We have photophysical events, which occur from some electronically excited state to the ground state of a reactant. And we have photochemical events, which stem from the electronically excited state, generally into some intermediate before arriving at our product state. Now, in this generic scheme, R, our reactant, is an organic molecule that absorbs a photon, h nu, whose frequency nu is correct for light absorption by R. R star is an electronically excited molecule and the essential species that is universal to all photochemical and photophysical processes. And finally, P is an isolated product or products. Now, to understand the photochemistry and photophysics of molecules, we need to consider two things. First, the electron configurations of two molecular orbitals, that is the highest occupied molecular orbital, HO, and the lowest unoccupied molecular orbital, LU. Also, the electron spin configurations of the electrons in HO and LU for the key structures R, R star, I, and P. So when a molecule R, our reactant, absorbs a photon of light to form a new product, it goes through a series of intermediates. The first being R star, our electronically excited state. Now we get to R star by promoting an electron from the highest occupied molecular orbital of R. We're promoting a single electron into the lowest unoccupied molecular orbital. So we end up with this intermediate state, R star, in which the HO level is half filled and the LU level is also half filled with a single electron each. And from these electronically excited states, we can form intermediates which are diradical in nature. And it's these diradicals that can result in products. Now, because this part of the course serves as an introduction to molecular electronic spectroscopy, the majority of this section will be focusing in on the electronically excited states and the deactivation pathways that these electronically excited states take as they return back to the reactant. And from these electronically excited states, we typically form intermediate species which are diradical in nature, where we have two half-filled non-bonding orbitals, which eventually will overlap to form sigma bonds and give you your final product. Because this section of the course is meant to introduce you to molecular electronic spectroscopy, the majority of our focus will be on the electronically excited states, R star, and the various deactivation pathways R star could take to return to the ground state reactant molecule. But in order to do that fully, we need to discuss the electron spin configurations of the electrons in the HO and LU molecular orbitals. So to further elaborate on the previous scheme, the electronic spin configurations of R star and I have been included. So again, overall, what we're interested in is the absorption of a photon by R to give us a product. We now know that there are various stages towards product formation, namely, once we absorb a photon, we form an electronically excited state, R star. This state then is transformed into some intermediate biradical state, and then eventually that will form our final product. Now, if we include the electron spin configurations of the electrons in R star and I, we get the following. As shown, the highest occupied molecular orbital contains two single electrons which have opposite spins, meaning they are spin paired. One electron has a spin quantum number of a -1/2, and the other a spin quantum number of +1/2. Upon the absorption of a photon, one of these electrons is promoted into the lowest unoccupied molecular orbital, as shown here. With that initial excitation, there is no change in the total spin of those two electrons, meaning that the electron that's promoted, as shown here, maintains the same spin quantum number, but now this electron is in a different molecular orbital. We refer to these two spin configurations as being singlets, and we'll describe that in just a moment. Now, there's another possible scenario based on the electronic spin configuration. If this electron undergoes a spin inversion or a spin flip, we now enter into a different electronic state, which is known as the triplet state, where the two electrons both the original electron of the HOMO and the electron that was promoted into the LUMO, these have identical spin quantum numbers, which is allowed due to the fact that these two electrons are found in different orbitals. Overall, this represents a different electronically excited state, the triplet state. And so let's summarize this slide in a bit more detail. So the electronic configurations of the ground states of R and P generally have the following form. There's 2 electrons in the highest occupied molecular orbital and no electrons in the lowest unoccupied molecular orbital. Now, according to the Pauli exclusion principle, the spins of 2 electrons in the same orbital must be paired. Anti-parallel spins correspond to a singlet spin configuration, or what's commonly known as the singlet state. The electron configurations of R star and I, both of which typically possess 1 electron in each of 2 different orbitals, are not required by the Pauli exclusion principle to be spin paired, meaning we can have both singlets and triplets. Thus, these 2 electrons in the half-filled orbitals can either be paired, singlet states, or unpaired. Parallel spins correspond to a triplet spin configuration or a triplet state. Now, singlet states are often given the symbol uppercase S, lowercase n, where n ranks the energy of the singlet state, starting with S0. So the subscript 0, this is reserved for the lowest energy electronic ground state, which is always a singlet state for ordinary organic molecules. So we refer to this lowest energy electronic state as the S0 or S0. The first excited singlet state is S1, the second excited state is S2, and it continues onwards. Triplet states are given the symbol uppercase T subscript n, where n again ranks the energy of the triplet state. Now, since the subscript 0 is reserved for the lowest energy electronic ground state, for triplet states, where the lowest energy state is a singlet, S0, we start with 1 and then go up to 2 and so on. So the first excited triplet state is the T1 state, and the second excited triplet state is the T2 state. So in the next video, we're going to look at the photophysical processes that involve the singlet and triplet states of molecules. If you have any questions about our introduction to photochemistry, by all means, send me an email. Thank you.